Hi, Dr. Mamori again, and I am going to perform the second experiment of the lab manual that you will be using at Central Campus of the Broward College. So if you're taking the class at Central Campus Broward College, you will be using this video to get the data for second experiment. Experiment 2 of the 1045 lab manual is published by Hayden McDean. You will see my name on it. It's the second, there is a fourth edition. Okay, the lab manual is specifically for Central Campus only. You will be purchasing for remote learning the ebook online from Vital Source, as I said, for my during my first video. So, for the first part of the experiment, this experiment is about physical and chemical properties of different substances, like elements and compounds, and we want to learn about the classification of the chemicals based on the physical changes of the matter and the chemical changes of the matter. First part of the experiment is saying that you do have these chemicals, which are like the elements, and you want to find their physical appearance, know about their physical appearance, how they look like, basically. At the end, you are going to come up with the differences between metals and non-metals. What are the common properties for metals? What are common properties for non-metals? So the first compound, the first element that you have here is carbon. I want you to look at the carbon because that's what you would do if you were in the lab, and I'm not sure that you expect me to do the experiment for you. I want you to do the experiment yourself. Some elements are okay to touch, others are not. So I can touch this, bring it out for you to see it even better. This is the carbon in the graphite form. So it's the same thing that you have in your pencil. So you are looking at this element and recording your observation, basically the color and the texture and any physical appearance that you would see. If it's shiny, is not shiny, what does it look like to you? Copper, so only the cupric color part. The other is like a copper that has been reacted over the time. They hold it in this container for the same experiment. So that's a sample of copper. We have another sample of copper here that it looks more like the copper for you. So record your observation based on the color and the look and the state, like it's solid, liquid, or gas. Was it shiny? Is not shiny? At least what color it is. Then you have iodine. I'm not going to open the iodine. Iodine is toxic, but I can tell you that is a solid, and you can record the color of the brown color solid. It's toxic and it's going to sublime as soon as I open it. It's going to sublime because it's a non-metal. Non-metals, they have very low boiling point, so it will sublime. I don't want to open it and inhale it. Magnesium, color of the magnesium again. It shines. It's shiny, and it's these are the pieces of the magnesium. It's kind of grinded, and so it's been grinded. We do have magnesium in different shapes also. Magnesium is very soft metal, so I'm just taking out so you could see that it is shiny, and it's very soft. You can break it actually by bending it. So this is your magnesium. So make sure that you record your observation, and you can break it. It's the metal that can break it. Not that I'm the superhero. Then you have the silicon, a white powder. So that is non-metal. So you are going to record your observation based on physical appearance and reading the procedure, what information you are going to record. So when you look at your When you read the procedure, everything that needs to be recorded, you are going to record based on what you see in this container for silicon. Then we have sulfur. Sulfur also is powder. This is also non-metal. It's powder. The color of the sulfur, yellow color, and it's not shiny. They're powder. Um, Last one, we have zinc. You saw zinc for experiment 1. We used to measure the volume. Zinc also is a metal. Sometimes the over the top, the outside of the zinc, it can get dull, but it's actually shiny. It's a metal also. One properties of metals versus non-metals. Metals are conductor of the electricity, conductor of the heat. And non-metals are not conductor. Non-metals are good insulators. And the procedure is asking to use the conductometer in order to, this is the setup for the conductometer in order to determine if they conduct electricity or not. The air is not a good conductor of electricity. What happens if something conducts electricity? This is a simple setup for the conductometer. If I plug in the conductometer into the wall power, when I plug it in, if air was a good conductor of the electricity, you see, you have the electrons coming in, but it's separate to two separate poles. You have 2 poles separated. If the electrons are moved from one pole to the other pole, then this light bulb is going to light up. If what you have between the 2 poles, they are not conductors, they are insulators, they are not good conductor of electricity, the light bulb is not going to light up. The samples that we have here, like we have zinc, we expect zinc to conduct electricity. And when we place the poles in there, I just want to show you what the problem is of not using this as excuse not to perform the part of the experiment. Is going to have air in between the particles. And as much as the sample wants to conduct electricity like copper, we know all copper wires for the wiring for electricity is made of copper. Is a good conductor of electricity. But if the 2 poles don't touch, they don't both stick to the copper itself, is not going to conduct electricity because the air, and this is not the right size of the copper for me to use it. So I'm just going to show you how the conductometer is working. Now, I'm going to unplug it because I'm touching the conductometer. I don't want to get electric shock here. And you witnessed that. I don't want that to happen. I have deionized water. Deionized water is a molecular compound. It's not a conductor of electricity. And if I turn it on, if I plug it in, the light bulb is not lighting up. And if I switch this with salt water, this is the salt water. I add NaCl, salt water, into the salt to the water. So I have salt water. Now I'm going to test the conductivity. So if the salt solution of salt in water is conductor of electricity, the light bulb is going to light up. You see how I just want to show you how it's working. It's not easy to perform the experiment with these pieces of metal. Definitely anything that is a non-metal is not going to conduct electricity. So for that part, you can answer the question based on the knowledge of how conductometer is working. And if your element is non-metal, like a silicon, and the sulfur is going to be, is not going to conduct electricity. But if they are metal, they will conduct electricity. So you can answer that part of the question yourself. Second part of the question, the second part of the experiment 2 is testing for solubility. That's another physical property. Polar general rule is that like dissolves in like. What does it mean? It means that polar compound or polar solute dissolves in polar solvent. Non-polar dissolves in non-polar. Water is the universal solvent, and it is highly polar. Organic compounds like acetone, hexane, it depends on the molecule. If they do have polar site and small number of carbon, then it's polar. Or if it dissolves in water, then it's polar. If it doesn't dissolve, it's non-polar. We can put it that way. Now, if non-polar compound doesn't dissolve in water, it would dissolve in a non-polar solvent. Let's say salt dissolves in water, so salt doesn't dissolve in oil. Oil doesn't dissolve in water. So we know that oil is non-polar, salt is polar, water is polar. So you can kind of go back and forth. So we are going to, or you can basically kind of expand your knowledge if you, by experience, you know, iodine did not dissolve in water. Oil did not dissolve in water. So most likely if you place iodine in oil, it would dissolve because oil is non-polar and iodine is also non-polar. So for the experimental procedure, first one, it says to mix water and acetone. So we are going to do for part 2, the first test tube is going to be mixture of acetone and water. It's asking for 3 milliliters of each to be tested of the 3 milliliters of the water and then 0.1 of the acetone. So we could put the 3 milliliters of the first one and use 1 milliliter of the acetone. Sometimes when they measure, when they tell you to do measurement, if you look at the introduction part of the lab manual, it also explains. If they give you like measure exactly 3 milliliters, then we have to use the exact measurement device. But if they tell you just measure about 3 milliliters, then it's going to be, it doesn't have to be exact. So you can do approximate measurement. So the first one is the acetone, second one is hexane. Going to do one experiment at a time, so we don't have to do, we can avoid labeling, or we have to label each one to make sure what they are, then it would be easy, it would not be easier for you to read the labels. So water acetone, we get the label for water acetone and then you back. Since it's the first time video recording these experiments, sometimes I don't know if it's going to work or not. So I say it's not going to work because see, it's not easy to read the label and other. Then it might be visible, so it's worth it to try. So we try to see if we can. Okay, 3 milliliters of water. So we measure 3 milliliters of water in test tube 1. 3 milliliters in test tube 2. And 3 milliliters in test tube 3. So I measured 3 milliliters of water and placed in each of these 3 test tubes. Then I'm adding acetone to 1. So I take the test tubes to, I will take the test tubes to the fume hood, and we can see there. I'll do this experiment and bring it back. I want to add 1 milliliter of acetone to water acetone and mix it well. So for you, you should see if this is like 1 layer or 2 layer. This is water with acetone. Okay? 1 layer or 2 layers. And if it's 1 layer, it might be easier for you to see with the dark background. 1 layer, that means is soluble. Do you see 2 layers, oil and vinegar like, or is just all in 1 layer? Okay, I hope that you can recognize yourself. To make sure this is the first time you're testing this, this is just forming 1 layer. If it was 2 layer, you would have seen a line here. Okay, for water acetone is 1 layer. Then we mix the second one. We are going to use hexane. Going to add hexane to second test tube. Hexane, the second test tube. See if the white background works better or black one. Which one helps? None? See, there's a line there, right here. And if you mix it, it's not going to mix and the line doesn't go away. So you have 2 layers there. When you have 2 layers, that means it's not miscible. So if it's not miscible, then it's not miscible, so it's not soluble. Have test tube next 3, water with naphthalene. So we're going to add naphthalene to the next test tube and try it. So as you observe the result of the solubility, you can right away conclude that acetone was polar because it did dissolve, and hexane was non-polar because it did not dissolve. Okay, this is naphthalene with water. See the solid and liquid. So for solid and liquid, it's easier to see because the solid state there, it didn't dissolve. So naphthalene did not dissolve in water. Now, next, we are going to test naphthalene with toluene. If naphthalene doesn't dissolve in water, it means naphthalene is non-polar and toluene is non-polar. So we're going to test and see if the naphthalene actually is going to dissolve in toluene. So we take the naphthalene, about 0.1 gram, very small amount, tip of the spatula. We take it and we add toluene for that one. And we have copper 2 sulfate and water. Copper 2 sulfate We add water. Okay. See blue color solution that was formed. The copper sulfate, because it's a soluble ionic compound, is polar. It did dissolve in water, but naphthalene did not dissolve in water. Naphthalene is floating on top also, and doesn't matter how much I mix it, it's nothing happening because it's non-polar. Then we have the naphthalene that I'm going to test it with toluene. Take you around the lab so you get to know the lab even though you're not here. Okay, this is naphthalene in water. I'm going to use gloves because I can't touch it without the gloves. Was the naphthalene with water? If I know it's water and salt, I was touching it, but with this compound is organic solvent. Okay, see what happens? The solid disappeared, and you can compare that to this. Water with naphthalene and toluene with naphthalene. See? Water with naphthalene and toluenes with naphthalene. Okay. Solubility part is done. Now we are going to look at the next part of the experiment. Start part 3 of the experiment. And for part 3 of the experiment, we want to test the copper sulfate. We have to heat up copper sulfate in a test tube over the flame. I noticed the gas was not working. So what I'm going to do, I'm going to take the copper sulfate, the blue color copper sulfate that we have here, put copper sulfate into a evaporating dish and place this on a hot plate. Going to place it on a hot plate, heat it up until I see a color change. Copper sulfate pentahydrate. That means there are water molecule that is trapped within, or it's part of the crystalline shape of this substance. So if you remove the water, it should change to different color. So the copper sulfate now is being heated on the evaporating dish. The procedure is asking for a test tube. The test tube is not safe or is not going to stay on the hot plate. That's why I chose the evaporating dish. The idea is not which container you use. The idea is when you heat up the copper sulfate, when it loses water, the powder is going to change from blue color to white color. And when we see the white color appears, then we stop heating and we continue with the next part of the next part of the procedure. While that is being heated up, I'm going to start or get ready for the second experiment of part 3, which is asking to add the sodium carbonate to DI water. Sodium carbonate. Okay. We bring the test tubes. The test tubes we have there. Okay, medium-sized test tubes. And while we are waiting for this, it's not hot yet. I have the crucible tongue to hold when it's hot. It's not hot. And in a test tube, I'm going to prepare the sodium carbonate solution while that substance is being sodium carbonate. I put sodium carbonate. Sorry, I had to tilt the camera to see. Sodium carbonate in a test tube and add about 6 milliliters of water. So we have the sodium carbonate solution here. In another test tube, we're going to have a solution of HCl. Sodium carbonate. Second test tube is going to be 1 molar hydrochloric acid. Okay. So maybe we can finish this part of the experiment. The hydrochloric acid, and then I have sodium carbonate in this test tube. I'm not holding because it's just like adding baking soda and vinegar. It's going to produce lots of carbon dioxide. It's showing a chemical reaction. So I'm just going to leave it in the test tube rack and just take a few drops of the HCl and add to the test tube. Okay. The bubbles that is forming is evidence for a chemical reaction. So we have a chemical reaction taking place here. Okay. If you remember the copper sulfate, the color for copper sulfate before, it was a darker blue color. That's the color. And now after heating, it changed to white color, much lighter color. Or if I continue heating, it would change to white color. But that is the color now after heating. Part of the experiment is asking what happens if you add two drops of water, deionized water, to the heated copper sulfate. So basically, the color, the center of this has the color with the water added, and then the side you have the color without before adding the water. So you could compare. It's going back to original color. Basically, you have the copper sulfate pentahydrate. After you heat it up, it changed to white color. That's losing water. You add the water back, and it gives you the color back to you. So because it's a reversible, it can be considered as it can be considered as a physical change instead of the chemical change, because it's reversible, the reversible part. The color change, it shows a chemical change because there's a color change. So the process is both chemical and physical. Okay. Copper, magnesium, and zinc. Next step of the reaction, we want to compare the next part of the procedure. We're comparing reactivity of the three elements for copper, zinc, and magnesium. We want to know which one is more reactive. One way to find out which one is more reactive is to make it react with the same reagent and look for the rate of the reaction. The rate of the reaction, meaning like how fast the reaction is going to take place. When the reaction is taking place fast, then we could see the color change fast. If the reaction involves formation of gas, we could see the bubbles forming really fast. So we could see those evidence of the reaction that is happening faster. Now, for this part of the procedure, we are going to make all three of them separately in three separate test tubes react with HCl, 1 molar HCl. HCl plus metal, if it reacts, it would give hydrogen gas. So you would see bubbles forming. The faster that bubbles form, that means that reaction is faster, and that translates to the element being more reactive. So for example, if zinc forms much faster bubbles, that means zinc is more reactive. If copper forms much faster bubbles, that means copper is more reactive. So let me label the three test tubes, place it here with the HCl, and then I add the metals to the HCl. I'm just getting the label for my test tubes. 1 and 2. Okay, I have the 3 test tubes, magnesium and copper, zinc with the 3 test tubes. I'm adding the pieces of metal to the first one, I'm adding the copper. The second, adding the magnesium, and to the third one, adding some zinc. So based on the fact that which one is going to form bubbles faster is going to be classified as most reactive. So I'm holding it against the camera so you can record your observation and your justification. The faster the bubble forms, that means faster reaction. And since the reagent is the same for all 3 of them, is HCl, a faster reaction means this metal that is placed in this test tube, which is the magnesium, is more reactive. So you can classify. And then we are done with the magnesium because so far we know that that is the fastest. I'm going to put the magnesium, and now we are comparing copper with zinc. For zinc, you see some activities going on, some bubbles are forming there. For copper, there is no activity. So that means copper, it's not reactive metal. And that's why for the plumbing, even they use copper that lasts for 30 years without being rusted or without being oxidized. So it's very stable metal. The only thing that would dissolve the copper is going to be concentrated nitric acid. So we are done with that part of the experiment as well. Okay, another aspect of the chemical reaction, which is the heat involved in chemical reactions. You want to know if the reaction is releasing heat or is going to absorb heat. If the reaction releases heat, by definition is known as exothermic reaction. The reaction that absorbs heat, by definition, is classified as endothermic type of reaction. So the last part of this experiment, for the last part of the experiment, we are going to mix the 2 chemicals with water, and we want to see the process of solubility of these 2 compounds is going to, and monitor the temperature. If the temperature it increases, we classify as the exothermic because it's releasing heat. let me add the chemicals to the test tubes, and then we add water. I'm going to use a thermometer since you are not here. Normally, we just have the students to touch and feel if the temperature goes higher or lower. But now that you're not here, I'm going to place the thermometer and give you the initial reading for the thermometer and look at the final reading. This way, you can have the feeling as you were here to monitor this reaction. Sodium carbonate and ammonium nitrate. So the two chemicals based on the procedure, one is sodium nitrate, sodium carbonate, and the other one is ammonium nitrate. Okay, sodium carbonate. I think using a second thermometer is better. So the initial temperature for both of them is going to be 24 as the initial temperature. So we have the initial temperature at 24. I measure the temperature of just pure water in a test tube. Now I'm going to add water to sodium carbonate and look for a temperature, and if the temperature changes, if the temperature goes up or goes down, I'm going to let you read the temperature yourself. So we start with the 24. Now you read this temperature. It's 30 degrees Celsius. That's your final temperature, or it might go higher even, but at least you see the increase in temperature. So sodium carbonate in water is an exothermic reaction because it's going to show the increase in temperature. Now I'm adding water to ammonium nitrate. Okay, adding water to ammonium nitrate, and I want to monitor the temperature. We start with the 24, and I want to show you how the temperature is going to change. With ammonium nitrate, it went from 24, so far we have 8, and it's still going down like 7. The point at this right now, we are not measuring the exact temperature. We are not trying to get the number for calculation. So all we want to know if the temperature drops or the temperature increases. Since the temperature drops for ammonium nitrate, then it means the ammonium nitrate solubility or of the ammonium nitrate in water is an endothermic reaction because it absorbs heat from water for it to dissolve. Okay, that was the last part of the experiment. For experiment 2, that's the last part, and you are going to collect the information by watching the video. At this point, you have watched the video. You record your data, And from your data, you are going to complete your worksheet or data sheet and turn it in as an assignment to your D2L. Thank you. We are done with the experiment, and I'm going to stop the recording at this